Okay, science projects using Radio JOVE data. Let's get into it. Uh, here's some experiment areas, and I included hardware in here, and Jim Sky's going to beat me about the head and shoulders. Really should be including software too. You know, we do science, but how do you do it? Well, you got to have hardware to get the data. You got to have software to manipulate the data, and then you got the data that represents something. But to do all those bottom bullet points, you really need hardware and software. So there's some general areas. Okay, back to hardware. You know, how do we get data? Well, you need instruments. How's that science? Well, you need to learn about the radio. You need to learn about the antenna. You need to learn about what polarization is and what radio waves are, and how are they produced in the first place? And all this data we get, I mean, what does it tell us about anything? Just learning the basics, well, that's science. Instead of taking it as received wisdom, go learn, figure it out, you know, see what you can do. There's some links at the bottom. I assume this will be published afterwards. Those links will take you to some really good resources. Real easy one for Radio JOVE people with just a single or a dual dipole. You can recapitulate Jansky and just look for the galactic hump. Or you can go pretty advanced and actually make a quiet day curve. The things that go hump in the night, basically you just take raw data every day for a year or so. You can use a single frequency receiver, or you can extract one or more channels from a spectrograph, average them together in frequency, smooth them in time, and then you look at when that galactic peak occurs in local, well, nope, I'm in the wrong one. Oh, in regular time, not LMST. But if you do that, you can calculate the length of the sidereal day. And that's an easy experiment to do. It's written up online. There was a JOVE newsletter about it. Pretty easy stuff, but really fun. Probably really great for a high school science class. Quiet day curve, that takes a little bit more. It's conceptually really easy. You log all your data in local mean sidereal time, and then you just do a bunch of averaging and histograms. You don't do a time series plot. You bin these things in 3-minute chunks, shove them into a histogram, and then if you look at the bottom left figure, that's 480 histograms, basically one sidereal day. Well, if you do that for 70 days, which is all the data I had at the time, you get the middle bottom plot, and then you just find the peaks. And what that gets you is the quiet day curve, you know, light curve, but it's quiet day. In other words, no RFI, no solar flares, nothing like that. That's useful to people like the ITU that want to know what the RF background situation is for communication channels. Something that could be embellished on this, this is only one frequency, 20 megahertz. You could make one of these QDCs for every frequency in a spectrogram. It'd take a lot of data and a lot of analysis, but you know, it's just grinding through it. Something else, you could also probably do it for 11, 12, maybe 15 years and see how the QDC changes with the solar cycle. And that would be interesting. But so much for the QDC. It's a pretty fun experiment. Learn a lot about Mathematica or Python or whatever data analysis package you're doing, but you get some neat results. And then can come to Jupiter. Jupiter's really, that's where my interest really lies. You can compare observations with other people. The CML-IO phase plane, that's some low-hanging fruit that is really, you could do some good stuff with that. And same with high-speed spectrograms. Now that we have the SDRs with Radio JOVE, we might be able to get some neat stuff from those that we weren't able to get with the FSX spectrographs, and definitely weren't able to get with the single frequency receivers. For observational comparisons, really what we're looking at here is the same Jovian emission as received by different stations. Well, that tells us, okay, probably ionospheric differences. How much is this going to tell us? I don't know. Without dozens or hundreds of observers, you probably can't infer too much about ionospheric conditions, except that, yes, Virginia, the ionosphere is different for different observers. But it's still fun to look at, and it's a good participatory exercise where people feel that their data is valued. And that's half the battle, as Nicole just explained. CML-IO phase plane, for those of you who don't know, it's a plane in phase space. Unfortunately, it's IO phase, so double meaning there. CML3 is basically the central meridian longitude system 3 of Jupiter. That's the magnetosphere's longitude. And on the vertical axis, we have IO phase relative to superior geocentric conjunction, which is when IO is directly behind Jupiter. It's at 180 when it's between Jupiter and the Earth. If you plot all the Jovian emission that we see, it was discovered that, oh, lo and behold, there's only certain regions that produce emission, or that have a higher probability of producing emission. So what you do, you take, an Excel log with 10,000 different observations, and you log when it happened and what frequency it's at and which polarization it is and all this data. And for each one of those storms, you can make a track on the lower left. You see it on the phase plane there. And if you sum all those up over time, and then you sum up all the times you were looking at Jupiter, and you divide the ones you saw by the times that you were observing, you end up with the plot on the right, which is a probability of when Jupiter would be in each of one of these 5-degree bins. These are 72 bins wide and 72 bins tall. And I can't see if you can see it. I got a bunch of people in the way, but the right-hand bar, I think goes up to 54% is the highest. And that's in IOC. IOB is almost there too. It's around 50% too. So any given day, you're looking for Jupiter, even when it's at opposition, even if you're dead center IOA, I mean, you only got a 30% chance that Jupiter's going to emit, unless the sun's active. And we'll get to that in a minute. So much for the phase plane. Here's the high-speed spectrograms I was talking about. These things are neat. Like the one on the left shows some fast drift shadow events in an N event. It was an IOCN event. And it looks like there's some S-burst train on the lower frequency edge of that. These spectrograms are only 2 megahertz wide. And these were made with a spectrograph that only had a 10 megahertz sample rate, but only used 5 megahertz of that because this was only real mode. These weren't complex samples. So this is something with an 8 megahertz sample rate SDR. You should be able to get these if you have a quiet observing site, which is 9/10 of the battle, we all know. But anyway, fast drift shadow events on the left and regular old S bursts on the right. These are what these things look like in fast time. Every pixel column here is about 200 microseconds, so 5 pixels wide is 1 millisecond. And that's pretty fast. But that's a fun thing too. And here again, had we 4 or 5 observers using SDRs, all observing the same event, how would S-bursts look different between different observatories? I don't know. They're pretty strong. The emission strength is really high, so that ought to be a good probe of the ionosphere. Of course, then your clocks have to be accurate to microseconds, but Larry Dodd can probably talk about that. He's the expert in timing. Anyway, on to solar stuff. Same thing. Comparing observations and how it relates to Jovian emission, and then solar eclipses, as Chuck mentioned. But here's one from just late May. This was the same Type 3 event. The SWPC didn't list any Type 2 there. It kind of looks Type 2-ish to me there, kind of on the right side, but who knows? It's kind of fuzzy definitions. But again, let people participate. Let them see how their data compares. Can we infer anything from the ionosphere from this? Probably. Quantitatively, don't know. That's tough. You got different antennas, different receivers, different locations. Got a lot of confounding factors there. One that this I haven't attacked yet, and this would be some low-hanging fruit for somebody. Sunspot number versus Jovian dam, or solar activity versus Jovian dam, or solar wind, or anything. If you look at the references at the bottom there, this stuff was looked at for about 30 years since the discovery of Jovian dam in the mid-50s. But really, for the last 40 years, I'm not aware of anybody having done anything with it. I think they just took Barrow's work and said, okay, this is what it is. Well, is it? And if you look at the graph on the right, back in the late 50s, early 60s, when Jupiter was just being discovered, they had great conditions. They had high Jovian D sub E. What is D sub E? I can't remember right now. Go ahead.
Declination of the Earth.
Jovicentric declination of the Earth. That's it. Mental block. It was out of phase with solar activity. So we all know high D sub E, 3 degrees. Boy, you're getting a lot of Jovian emission. Negative D sub E, 3 degrees negative. We don't see a whole lot of Jovian events here on Earth. Well, over the intervening decades, now we have high D sub E, but we also have high solar activity. So if we see an increase in Jovian dam being observed, well, is that due to solar influence, or is that due to high D sub E? I'm not sure how you'd eliminate the confusion there, other than waiting another 100 years for it to go back out of phase and then look at the previous 200 years data, but I'm not going to live that long. But it still would be a really cool analysis to do. And here's one thing Chuck mentioned earlier, solar eclipses. This was the one from 2017. This was, you could see AJ4CO in Florida there, and Eglon's on the map because they had a rheometer at the time. And the black circle, little black dot, that's totality at closest approach to the station. The gray area is the amount of attenuation of solar radiation on the D layer was 90% attenuated, so 10 dB down. And then the light gray circle, that's the 7 dB contour. It was 80% down on the F2 layer, given the geometry of the shadow and the height of the ionospheric layers. The plot on the right, I don't know, I think it's interesting. The top purple line is that D layer attenuation as you approach, or as the shadow approached the station and then moved away. But in the red data, that data has been smoothed a little bit. There's two peaks, one leading the closest approach and another peak after. It's like what we saw at 20 megahertz dipped in advance of the solar eclipse's closest approach. But AJ4CO wasn't the only one to see that. Wes Greenman saw the same thing, and I believe Francisco Reyes saw the same thing too. We never really did much more with it, but here it is, and that's half the problem with citizen science. You get all this great stuff, but you got to take it that last mile to get at least a write-up or a paper or something published about it. But here again, solar eclipses, fun stuff. Got to write it up though. Yay, mea culpa. Extrasolar emission, here defined as anything coming from outside the solar system. You've got a couple point source emitters, Cas A and Sig A. Cas A is a supernova remnant, and Sig A is an active galactic nucleus. When you look at them in a spectrogram, scintillation, since it's related to frequency because of the way the radio waves react with the ionosphere, depends on frequency. You end up with these curved lines and shadows in a spectrogram that you see on the right. This was with an 8-element array actually aimed northward at Cas A. You can see from the middle figure is radio eyes, and the antenna beams that oval in the right centered on Cas A. This has been up a couple times. We did it in 2014, and then another one with Richard Flagg and Jim Brown did it again just a few years ago. Interesting enough, as y'all know, Cas A, its emission is decreasing over time. That's why you can't really use it as a calibration source. But it's to the point, I don't know if it's flipped now, where Cas A is weaker than Sig A. They were thinking it would, but then the decrease slowed down for a little while. So I'm not sure if we're to the point yet where they're absolutely equal or not. I'm not sure anybody actually knows yet. It's still kind of up in the air, still being observed. So if you had a calibrated Radio JOVE setup, and you had a clear radio frequency, and you're really good with amplitude calibration, probably make some contribution here at HF band frequencies to the absolute spectrum of Cas A or Sig A. Going to take a lot of data, a lot of nights, because you've got to average. You can't rely on scintillation, because scintillation artificially increases the aperture, the effective aperture of your antenna, because the ionosphere is a lens basically, but a dynamic one that isn't constant. Anyway, so much for extrasolar emission. I don't know of anything else. You're not going to detect any Jupiter class extrasolar planets. They were trying to do that with the UTR-2, which had what, 2040 fat dipoles over there in the Ukraine until the Russians bombed it. So that, and they didn't see anything. We're not going to see anything with 2 narrowband dipoles here. Terrestrial propagation is another thing we can look at with Radio JOVE. It's kind of iffy whether it's radio astronomy or not, but hey, whatever. It's still science. We kept seeing these teepee-shaped figures in our spectrograms, like about a decade or so ago. And we just got to thinking, well, is that distant lightning making one or more hops? Xing Feng got involved and did a lot of the math. Thank God for that, because that was a little beyond me. We wrote a paper about that and actually got it published in GRL about what these teepees really are. And that came from Radio JOVE data. So there's some actual, what you would call real science. I don't think the word real applies. I think everything we do is science, but this would be what a lot of people consider real. Something else with terrestrial propagation, HARP did an experiment where they were pinging the moon at 9 megahertz or so, 9.6 megahertz. And I thought, well, let me radar range the moon. Why not? So I strung up a single 9.6 megahertz dipole, connected it to a JOVE receiver, a special one for that frequency. Still JOVE stuff nonetheless. And we did the timing, and it didn't work out the way I thought. We knew where the moon was, to an inch, to a millimeter. And we know where HARP is, and we know where the AJ4CO station is. And it turned out that the paper really shouldn't have been how to radar range the moon. It should have been how to measure the propagation time between Alaska and Florida, which was anomalous. It was much longer than we expected. If you assumed 2 hops, the signal should have got to Florida a lot quicker. But thinking, okay, HARP's beam was aimed pretty high above the horizon. Most communications antennas are aimed right at the horizon to give you that low takeoff angle and get a nice long hop going. Well, it is closer to NVIS, near vertical incidence skywave. Not quite, of course, at 45 degrees, but still same idea. So we're thinking maybe 13, 15 hops from there to Florida. So it's an open question what this data is actually showing. But the fact we were able to integrate the signal over time, get some nice humps that you could get actual blips out of, and actually radar range the moon. That's pretty cool. Here's one that Whit Reeve really gets into up there in Anchorage. Sudden frequency deviations works kind of the same way as that lunar ranging. What you're doing is looking at WWV, and then you're looking for Doppler shifts. And these Doppler shifts have 2 main sources, one mainer than the other. The most important is the height of the reflection layer. As that layer gets lower, you'll see a momentary increase in frequency. And on this plot, the way that software Argo plots things, a negative going trace is actually an increase in frequency. So think of it as a decrease in wavelength. The other way is if the refractive index of the ionosphere changes, that's also going to increase or decrease the observed frequency temporarily. So what these plots are showing on the left is a solar event, an X-ray flare, and its effect momentarily on the observed frequencies of the WWV transmitters at, I believe this is 15, 20, and 25 megahertz. Yep, even says so on the slide. All right, what else we got? Well, I guess that's it. We're done. Little further reading for people who want to actually ask the questions and get into the science and actually do the science and learn things. So thank you, everybody. Are there any questions?
Very good. Thank you. We have a question. Anybody have one?
I have one.
Go ahead.
I'm curious with these projects you're showing, there must be somewhere a community of solar physicists who spend all their time studying the sun and developing theories about the sun and writing about the sun. Do those people have some kind of relationship with the Radio JOVE project?
Not that I am aware of. Chuck may contradict me, and I hope he does. We approached some people from the SWPC at the last JOVE SARA conference back in 2014, and it was bandied about that, yeah, let's work together. They were quite excited about our data. But it kind of died on the vine. We tried to follow up. Nothing much happened. And of course, now with the budget cuts and the federal government taking rheometer after rheometer offline, I don't know if they have the resources to do anything or not with us, but that's just the SWPC. There's got to be a lot of other solar plasma physicists and solar weather experts out there that could use this data. Chuck, do you know of any relationship? I'll throw it over to you.
The Xing Feng at NASA Goddard works in the heliophysics group, so he has some contacts there. And then the Sunrise GRL that we've formed that relationship. So that's another way that we may be able to move forward with this.
Okay, thanks again, Dave.
Thank you, everybody.